Today we're going to get our first taste of factoring. Specifically, we're going to be using the greatest common factor. But before we do that, I want to take a step back and think about where we've been with our polynomial operations. So let's consider the multiplication x times 3x plus 7. So what we know about multiplication is we can apply the distributive property here, right? And so x times 3x becomes 3x squared, and x times 7 becomes 7x. So if we look at the two terms in this binomial that we've created, if we think about what those individual pieces are, 3x squared and 7x, each of those two pieces have a greatest common factor of x, right? 3 and 7 have a GCF of 1, and x squared and x have a greatest common factor of x. So 1x, or simply x. And if we think about where that might have come from, and we look at what we're left with, if our greatest common factor, x, is out in front of this polynomial, then the 3x and the 7 are the pieces that are left behind. And so when we think about factoring, what we're doing, factoring is the process of rewriting a polynomial, zoom out just a little bit, as a product. And so essentially what we're doing, the long story short, is that we are undoing multiplication. So the idea with factoring, and specifically factoring with the greatest common factor, is that we're going in reverse. Instead of starting with the two polynomials that get multiplied together, we're going to be starting with the final version and working backwards. So that's kind of our long story short with factoring. So we're working backwards. Now, factoring is not quite the same as division. I say it's undoing multiplication, but it's not exactly the same thing as division. That will come later. Just as a heads up, some polynomials cannot be factored. If they cannot be factored, we call them prime. Just like prime numbers, right, have nothing to be factored other than 1 and themselves, polynomials can also be considered prime. So we're going to do some examples to see how we might approach this. So our first example, 3x plus 12. And I'm going to start by thinking about the GCF of 3x and 12. Well, 3 goes into both 3x and 12, and then the x is not common to either of them. So our greatest common factor is 3. So I'm going to start there. Now, I take my greatest common factor out, and then I open these set of parentheses, and what goes inside of these parentheses is kind of like the leftovers. If I take a 3 out of 3x and I take a 3 out of 12, what will be left behind? Well, 3x and x would make that 3x, and 3 and a positive 4 would make that 12. So I get my factored version is 3 times x plus 4. Now the great thing about factoring here is that we can always check this by actually multiplying, back through, as long as I write it correctly. So if I multiply 3 times x and 3 times 4, I get 3x plus 12, which is what I started with. So really the two steps here. The first step is to identify your greatest common factor and then identify your leftovers. And I would say that your third step is to check, did you do it right? If we have the ability to check, we might as well do that. So we're going to do a few more examples. Some of these I will do completely with you, and some of them I will have you try out on your own. So 7y minus 7, again, I'm going to start with what is my greatest common factor of 7y and negative 7? Well, y is not in both of those terms. The only thing they have in common is a 7. 7 times y makes 7y, and 7 times -1 makes -7. So when I factor this, I'm going to bring my greatest common factor out in front, and then I'm going to open my parentheses to think about my leftovers. Another way to think about this is what would I have to multiply by to make my original expression? So for instance, 7 times what makes 7y? Well, 7 times y makes 7y. Then 7 times what makes -7? Well, -1. So we get a factored version of 7 times y minus 1. And again, I want to check. 7 times y minus 1. Do some distribution. I get 7y minus 7. And that's what I want. So example 3, again, we're going to start with what is our greatest common factor of these two terms. 6a squared and 27 have a greatest common factor of 3. So I'm going to start there, factor out my 3. 3 times what will make 6a squared? Well, 3 times 2a squared will make 6a squared, and 3 times 9 will make 27. And again, we love to check. Do some distribution, we get 6a squared plus 27. Notice it took me all of, 5 seconds to check my answer. So, you know, as with everything, you're probably going to make some mistakes. You're probably going to do something silly that you didn't even mean to do. As long as we're checking our answers, we can catch those mistakes and fix them. So 4y squared and 24y, again, starting with that greatest common factor. So the greatest common factor of 4y squared and 24y is 4y. The 4 and the 24, that's pretty obvious. We get a 4 out of that. And if I just need a little reminder, y squared is y times y, and y by itself is just y. And what they have in common is a single y, and that's why that's in our greatest common factor. So I'll have 4y out in front. And then inside my parentheses, again, I'm thinking either what are the leftovers if I took out 4y, or I can think of what would I have to multiply by to get back to the original. So 4y times what makes 4y squared? 4y times y makes 4y squared, and 4y times what makes 24y? A positive 6. Make sure you do have a plus or minus there, right? If I have a plus or minus in my original, I should have one in my remainder. That's another word I might use here is remainder, the things that remain. So if we were to check this, we would be on the right track. Just a couple more here to really reinforce this. So 15a and 30ab will have a greatest common factor of 15a. 15 goes into both 15 and 30, and then they both have an a, only the second term has a b. So when I factor out 15a, I'm going to be left behind with the expression 1 minus 2b. Now, it's really important that I have that 1 in there because a lot of times we'll think about, oh, I took out a 15a, right? That means that there's nothing left, right? There's nothing left. But that's not quite true because if we were to think about it as just 0, or maybe if we tried it as, oh, 0 minus 2b, when I checked and did that multiplication, 15a times 0 is 0, and then we would have that minus 30ab, and that 0 does not match what we were looking for. So we do need to keep that 1 in there to match through multiplication. It's a multiplicative relationship here. It's not an addition or subtraction. So be really careful there. That's a pretty common mistake. One more example. This one has 3 terms in it, which always makes it just a little bit more challenging. So remember, when we're thinking of the greatest common factor, we can think of the coefficients, the numeric coefficients first, and then we can also think about the variables here. So x to the 4th is x times x times x times x. X to the 3rd is x times x times x. X squared is x times x. And so it looks like all 3 terms have x and x, or x squared, in common. So our greatest common factor here will be 3x squared, because 3 is the numerical greatest common factor, and then x squared goes to the variable. So factor out 3x squared, and then I think about what remains. So 3x squared times what will make 12x to the 4th? Well, I need 4x squared. 3 times 4 makes 12. X squared times x squared makes x to the 4th. Okay, 3x times what will make negative 9x squared? Well, I need, a negative 3x to get my negative 9 and my x to the 3rd. And then the last piece here, x to the power, 3x squared, yikes, times what makes 24x squared? That would be a positive 8. And again, if I just wanted to check this with multiplication, it would turn out exactly the way we need it to. So even though I haven't walked through the multiplication process here in the last few examples, I really encourage you to do that as you are doing these practice problems yourself. So let's do just a quick recap, because I know it's helpful to have a roadmap here. So if we are factoring using the greatest common factor, I would look at the coefficients first, right? The numerical part of that, and identify their greatest common factor. So start with the coefficients and look at the numerical greatest common factor. And then remember that a variable must be, a factor in all terms in order to be a part of the GCF. So if for instance one term has an x and the other one doesn't, remember then x is not a part of the greatest common factor. That variable has to be in every term. So if a variable is in all of the terms, like we said when we first reviewed the greatest common factor, is we take the one with the smallest exponent for the greatest common factor. And a good example of that is example 6 from up above, where we did have x's in all 3 terms, but the smallest power was a power of 2, which would be the most that they could possibly have in common. And so we put that power of 2 in our greatest common factor. So if we look at the coefficients, we look at the variables, and we find our greatest common factor, then I'm putting the word divide in quotation marks because we're not exactly dividing, right? But we're taking out the GCF to get the remainder, or the parts left behind inside the parentheses. And remember, another way to think of this is to ask ourselves the question, what do I need to multiply by to get back to the original? So again, if I take out my GCF is out. The question then becomes, what's left would be the thing or things I need to multiply by in order to get back to the original expression. So just a few more examples here, because I do think it's helpful, and some of these examples are going to get a little bit more complex, but that's what we're doing them all together for. So number 7 here, 10x squared y squared minus 8xy. So we need to start by asking ourselves, what is the greatest common factor? So the greatest common factor between our coefficients, right? We're starting with the coefficients, 10 and -8 is 2, right? That's the largest number that goes into both 10 and -8. And then thinking about, okay, x squared, y squared, and xy. Clearly they both have x's and y's. X squared, y squared is x times y times y. And xy is just x times y. And so when I look at where they overlap, they have x and y in common. And I do want to show you a little bit of a shortcut once you have your GCF and you start to factor that out. If you think about the remainder, the coefficient's the easy part, right? 2 times, 5 makes 10. So I can do that part. The variables do get a little bit trickier. But take a look at this. Take a look at what we have left over up above. If we took out that x and that y as the GCF, we have an x and a y left over. So we have an x and a y in our remainder. So that might be another shortcut for you to use. When it comes to that second term, we need 2 times -4 to make that -8. And then we don't have any variables left over, right? We took out both of those x's and the y's. So our factored version is all done like this. And again, we can check by multiplying. So a couple more examples here. Looking at 5x minus 13y, my greatest common factor. So 5 and 13, or 5 and -13, have a greatest common factor of 1. And then x and y, those are not the same variables. So actually, 1 is our greatest common factor. Now, what happens if I factor out a 1? Well, my remainder doesn't change, right? I need to multiply by 5x and -13y to get back to my original. So I could actually call this one prime. This polynomial cannot be factored any further, right? It's done, it's prime. So remember, that is a possible outcome here. Okay, 2 more examples. Let's look at 6a to the 4th plus 14a squared minus 10. Again, starting with our greatest common factor. In this case, it is 2, right? Even though we have a to the 4th and a squared in the first two terms, we do not have a at all in the third term, so we can't include that variable. So I factor out a2, and then my remainder, again, is what do I have to multiply by to get back to the original? So 2 times what makes 6a to the 4th? Well, 3a to the 4th would get me 6a to the 4th. 2 times a positive 7a squared, and 2 times a -5 would get me -10. And again, do not lose those operators, the addition and the subtraction. If you have operators in your original, you need to have operators, and when I say operators, I mean addition or subtraction, in your remainder. All right, last one, best one. This one's 3 terms. We got multiple variables. It's going to be a good one. So our greatest common factor is going to be 2xy. So again, starting with the coefficients, 2, -2, and 4 gives us the greatest common factor of 2. And then if I need to expand my variables here, that's fine. That visualization is really helpful. That's why we're using it. So x times y is x squared y. Xy squared is x times y, and xy is x times y. So when I look at what they have in common, all 3 of them have an x, and all 3 of them have one y. So that's why xy is a part of our greatest common factor. And then when I factor that out, settle down, 2xy times what will get me back to my original. And again, remember we have some variables in our remainder there that can help us. So 2xy times x makes 2x squared y. 2xy times a negative y gets 2xy squared. And 2xy times a positive 2 gives us 4xy. So this is going to be a little bit harder than just finding the greatest common factor. But remember, with all of these, we can check by using multiplication. You will make a mistake at some point, but the best part about making mistakes is that you can fix them. So thanks for tuning in. Do your best and let me know if you need anything.